Now that we know how to write electron configurations, let's talk briefly about some exceptions. So let's consider the two elements chromium and copper. What are the expected electron configurations you would think that these two would have? Well, if we were to reference argon, we would expect chromium to have an electron configuration of 4s2, 3d4. And for copper, we would expect, referencing argon, to have a configuration of 4s2, 3d9. So with these two, notice that the d is 4 or 9. And recall that a d subshell can hold 10 electrons. So these two are one away from either being half filled, which would be this case, or completely filled, which would be this case. So they're one electron away. So what actually ends up happening on its own, naturally, is one of the electrons from the outer 4s region will actually drop in to the d subshell, and thus will create the configuration 4s1, 3d5 for the case of chromium, and 4s1, 3d10 for the case of copper. Are those the only two elements that have this exception? No. It's also true for the elements that are below them on the periodic table. So if you take a look at chromium, the three elements that are below it are Mo, W, and Sg, and copper have the elements Ag, Au, and Rg below. So remember that when you're doing those configurations, in other words, when you get a configuration where you're either D4 or D9, it will pull over one electron. Make sure you know that, because if you do this on the test, it will be marked wrong. You need to make sure that you draw it or write it out with the one less electron. All right, let's talk about valence electrons again. In the last video, we briefly mentioned it, but reminder, valence electrons are the most important electrons in chemistry because they are not only the outermost, but these are the electrons that are actually involved in chemical bonding. When you take a look at an electron configuration, such as these two here, you can actually figure out how many valence electrons there are. Just look at how many electrons are in the outermost region. In the case of the first example, it looks like 2 is the highest energy level, meaning it's the furthest out from the nucleus. Well, how many electrons are there? Well, we have 2 from the S and 6 from the P. So total, there would be 8 valence electrons in this example. In the example below, it looks like 3 is the farthest energy level from the nucleus. So how many electrons are there? Well, there's 2 from the S and 5 from the P. So in that example, there are 7 valence electrons. Now, that's one way to figure out valence electrons, but there's probably an easier way. If you're looking at the main group elements, which are essentially the elements that the columns are higher on the periodic table, meaning they're not the transition metals, then look at the Roman numeral number group that the element is in. That will tell you how many valence electrons there are. For example, oxygen is in group 6A, so it has 6 valence electrons. And if we were to write out the electron configuration for oxygen, we could confirm that. As a reminder, or not a reminder, but a further evidence, the ones that we solved up here, what element is this first one? This first one is neon, right? And neon is in group 8A, which means 8 valence electrons. This second element right here is chlorine. And chlorine is in group 7A, which means it has 7 electrons. This will help us figure out how many valence electrons that a main group element has. So let's do some practice. How many valence electrons do the following elements have? And this can be filled out in example 15. Magnesium is in group 2A, so it has 2 valence electrons. Nitrogen is in 5A, so it has 5 electrons. Potassium is in group 1A, so it has 1 valence electron. Now, helium is an exception. Helium is in group 8A because it's a noble gas, but helium actually only has 2 valence electrons. Because what's the configuration for helium? Just 1s2. And so, since it doesn't have a p block, 2 is the number of valence electrons it has. And then finally, chlorine is in group 7A. It has 7 valence electrons. Well, that's for main group elements. What about transition metals? Well, let's think about it. And let's go back to some examples here. If we were to look at these examples that I have here, and of course I have just butchered them, but if we were to look at the electron configuration for these elements. Let me write them out real quick. Nickel would be, referencing argon, it would be 4s2, and it would be 3d what? Let's see, 3d8. Well, what's the highest energy level? It's 4, right? 3 is not further out than 4. 4 is the outermost energy level. So there's only 2 electrons there. So 2 is going to be the number of valence electrons. And actually, think about it. All transition metals, or almost all transition metals, will have 2 valence electrons. Because if you take a look at your periodic table, look at where the transition metals are. You'll always get through those 2 s electrons, but you'll never get to the p electrons. So the maximum that there can be is 2. But be careful. Remember your exceptions, like copper, for example. Copper was 4s1, 3d10. So in the case of copper, 4 being the highest energy level, there's only that 1 valence electron. So almost every transition metal will have 2 valence electrons. Just make sure you watch out for your exceptions that we went over in the previous slide. Alright, so we've been doing electron configurations for ions. How would the electron configurations look if we were looking at, or we've been looking at electron configurations for atoms. What would they look like for ions? Well, elements want to be just like noble gases, because if you think about it, noble gases have all of their orbitals completely filled. They're stable. And so that means that their outermost shells are going to be filled, which means 8 valence electrons. So every other element that's not a noble gas will either lose or gain electrons in order to become like noble gases. That's why they become ions. So we need to keep track of that loss or gain of electrons when we write the configurations. Let's take a look at just an image. Let's take a look at the configuration for sodium and for chlorine. Sodium's electron configuration is here. Notice that it has 1 valence electron. And we also could have figured that out based on what group it's in. Chlorine's electron configuration is here. And notice how many valence electrons it has. It has the 2 plus 5, so it has 7 valence electrons. And once again, we could have figured that out based on the fact that chlorine is in group 7a. Neither one of these elements are happy because they don't have their full 8 valence electrons like a noble gas would have. So sodium. Do you think it's easier for sodium to lose that 1 electron or to gain 7? The answer is it's easier to lose that 1 electron. So if sodium were to lose that 1 electron, notice first of all what happens. Its resulting electron configuration would be 1s2, 2s2, 2p6, which is just like neon. It has now achieved its noble gas configuration. But also, if sodium lost an electron, it lost a negative particle, then that results in the sodium ion. On the other hand, chlorine. Chlorine has 7 valence electrons. Do you think it's easier to lose those 7 or to gain 1 to become like a noble gas? It's easier to gain 1 electron. And so, chlorine would most rather gain an electron, therefore taking it from 3p5 to 3p6, which is the same configuration as argon. What happens when chlorine that was neutral gains a negative electron? It now has a -1 charge. And by the way, sodium wants to give up an electron. Chlorine wants to take an electron. It kind of makes sense that Na and Cl are good partners, and that's why the compound sodium chloride exists. So knowing that, let's figure out, to help us out, what charges each group of elements would have. As a reminder, we can figure out how many valence electrons there are from what group it's in. So 1a has 1 valence electron, 2 valence electrons, 3 valence electrons, 4, 5, 6, and 7. So, group 1a elements, they would like to give up 1 electron, right? That's easier than gaining 7. So if they gave up 1 electron, that's going to result in a +1 charge. And by the way, I would write these at the top of the groups on your periodic table. So group 1a elements will create a +1 charge. Group 2a elements have 2 valence electrons. It's a lot easier to lose those 2 electrons than to gain 6, right? So if they lose 2 electrons, 2 negative particles, they will become positive 2. For the same reason, group 3A elements will become positive 3. Now group 4A elements, will they lose 4 electrons or gain 4 electrons? Both seem equally plausible, so this group actually is plus or minus 4. Now once you get down here, 5 electrons, it's easier for these elements to gain 3 electrons than to lose 5. So if group 5A elements gain 3 electrons, they're gaining 3 negative particles. They're going to be a negative 3 charge. These elements in group 6A, which have 6 valence electrons, are going to gain 2 electrons to make it negative 2. And finally, group 7A will gain 1, making it a negative 1. So now I could ask you, what charge would a certain element be most likely to have? For example, let's take a look at some. What about calcium? What charge does calcium usually would have when it becomes an ion? Well, calcium is in group 2A, so it would have a plus 2 charge. What about sulfur? When sulfur becomes an ion, what charge would it have? Sulfur is in group 6A, so it would have a negative 2 charge. This is how we use this information. All right, so this is a good time to bring up something called an isoelectronic series. It sounds really fancy, but what does that mean? We've been talking about this idea of elements want to become like noble gases, right? And so they gain or lose electrons to do that. Going back real quick, for example, and let me clear up some space here. What did the sodium ion and neon both have in common? The same electron configuration. In other words, the same number of electrons. But what is different between them? Their number of protons and neutrons inside the nucleus, right? So keep that in mind. When we talk about an isoelectronic series, we are talking about elements that all have the same electron configuration as a noble gas. They have the same number of electrons. But they're not the same size. Why? Because they have a different nucleus. Don't worry about this terminology right here. They have a different nucleus. They have a different number of protons. Let's look at neon, for example. Neon is our noble gas. And if we think about the fluorine ion, the oxygen ion, the sodium ion, and the magnesium ion, all of these species have one thing in common. They all share the same electron configuration. They all will have the same configuration of 1s2, 2s2, 2p6. Great, they all have 10 electrons. But what do they not have in common? Their nucleus. Oxygen has 8 protons, fluorine has 9, neon has 10, sodium has 11, and finally magnesium has 12. Because magnesium has the most protons, because of that, those protons will be able to pull the electrons in tighter, ultimately resulting in a smaller ion. And because oxygen has the least number of protons out of all of them, oxygen will not be able to pull the electrons in as tightly as the other 4. And oxygen, therefore, will be the largest. How do you know a series is a group of elements and ions are isoelectronic with each other? Take a look at the noble gas. In this example, it's neon. If you look at your periodic table, what are the elements leading up to neon? Fluorine and oxygen. What are the elements directly after neon? Sodium, magnesium. So you'll know a set of ions is isoelectronic because they're all elements that wrap around the same noble gas. So that's a way you can figure it out. And once you know a set of ions is isoelectronic, the one that is going to be the smallest is the most positive. And the one that's going to be the largest is the most negative. Such as oxygen's -2, magnesium's +2. That corresponds to what we just talked about here. We'll continue on with writing electron configurations for ions in the next video.